So a block of mass little m at the top of a hill of height h is compressed against a spring with spring constant k. It travels down the hill and collides with an identical block at rest. The two blocks then travel together and compress an identical spring, same spring constant there. If the spring at the bottom of the hill is compressed a distance s, so this is going to be squeezed in s, how much was the spring compressed at the top of the hill? So we have a lot of different pieces that are happening. We have compressed springs, so you should be thinking energy or some kind of force, probably energy in this case. So we're thinking energy. Okay, and then so we have spring potential energy. It's going to get released. It's going to get converted into kinetic energy because it's going to start moving. Then it's going to gain more kinetic energy because as it falls, the gravitational potential energy will get converted to kinetic energy, and then we'll have a collision. The collision part is where we would do momentum. So a lot of times collisions we do conservation of momentum. Okay, so we'll do a conservation of momentum here, and then whatever energy is remaining will then get converted into compressing that spring. Okay, so let's say this spring, what we want to know is how much it's compressed at the top of the hill, the initial compression that I'm going to call x. So we want to do energy over this whole motion. So at the top here, we want to think about its energy. It has a elastic energy, plus it has some gravitational potential energy. Now, it doesn't have any kinetic energy because I've just compressed the spring. I'm holding it, and then I'm going to release it, let it go, right? So it's released, it travels down, collides, and then, yeah. So right before the collision, all of that energy is converted into kinetic energy. Okay? So we would say there's no energy being lost because they didn't say frictionless, but we'll assume frictionless. 1/2 kx squared plus mgh is equal to 1/2 mv squared. Okay, and then we can solve for this velocity here. We're going to use that velocity during the collision part, right? So I'm going to multiply by 2, so that gets kx squared plus 2mgh equals mv squared, and then divide by m to cancel that guy out. And then take the square root. So the v is going to be the square root of kx squared plus 2mgh over capital M. Then we're going to do momentum conservation. So if you look at these two blocks, okay, as they collide, their momentum is conserved. This guy is a momentum mv, and then this guy has no momentum, right? So before the collision, the momentum is just mv, and then afterwards, they move off together with 2m times, we'll say, some other velocity v2. Okay, so that means, mv, the momentum before, has to equal the momentum after by conservation of momentum. And so v2 has to be 1/2 of v, right? Just divide both sides by 2, which we know is 1/2 times the square root of this, right? Okay, and then lastly, we're going to say the kinetic energy here of the two object system then compresses the spring in S. So we're going to say the kinetic energy we have here of the two blocks moving together gets converted into the spring potential energy, which is 1/2 kx squared, where how much is compressed in this case is S. Okay, so we're going to say that 1/2 times 2m times v2 squared, that's the kinetic energy here, has to equal 1/2 k s squared. The 1/2s can cancel, and then we can plug in, we can square this thing and plug it in here. So this is 2m. When I square the 1/2, I get 1/4, and then this becomes kx squared plus 2mgh over m is equal to ks squared. And then our goal is to solve for x. I want to know what the initial compression was. So the 4 and the 2 cancel to 2. These m's are going to cancel. I'm going to multiply both sides by 2. So I get kx squared plus 2mgh. Multiply this by 2 to get 2ks squared. And then subtract the 2mgh. Kx squared is equal to 2ks squared minus 2mgh. And then just divide by k. and then finally take the square root to solve for x.